Well, good afternoon. Thank you everyone for attending today's webinar, Meeting Tomorrow's Challenges with Aluminum Extrusion, brought to you by the Aluminum Extruders Council and Design World magazine. Just a couple of housekeeping details before we get started. You should ask all questions related to the webinar in the Q&A box, and answers will be asked during the remaining time. If we did not get to your answer, our presenter may reach out to you afterwards. The webinar slides, as well as additional resources, can be found in the resource box. We do encourage you to tweet with us. Simply sign in through the Twitter box, and today's hashtag will automatically be added to your tweets. Now, if you have any questions on the On24 system, or if you need any sort of help, please just refer to the help widget on the bottom of your screen. If you're watching this on demand later on, you can still use all of the features that I just went over. And lastly, there is a bio widget with the presenter information, including emails. My name is Paul Heaney, and I am the VP Editorial Director for Design World. A little background on me. I have a mechanical engineering degree from Georgia Tech, and I've been covering the engineering and manufacturing worlds for more than 20 years now. I am pleased to be your moderator here today. I'd like to take this opportunity to thank our presenter for being here today and to introduce him. Jason Weber is the VP Sales and Marketing for Tabor Extrusions. He has more than 20 years of global manufacturing experience collaborating with internal partners, end users, suppliers, and international partners to help innovate product and service offerings. Jason is an active member of the Aluminum Extruders Council, and he is the leader of the Council's marketing/industry promotion team. He has a Bachelor of Science degree in Business Administration and Marketing from Minot State University in North Dakota. And so without further ado, I will hand the mic over to Jason.
Thanks, Paul. Good afternoon, everyone. Again, my name is Jason Weber with Tabor Extrusions. On behalf of the AEC and Tabor Extrusions, I'm thankful you were able to join the webinar today. The Aluminum Extruders Council is the governing body for the aluminum extruders with over 60 extruder members, accounting for 75% of the extrusions produced in North America. We focus on user education as well as member business excellence, and also have an active fair trade committee that works a lot on a variety of issues regarding trade and global issues today. Tabor is an AEC member with 2 locations in North America. We've also just added a new line of micro extrusions to accompany our large and medium-sized shapes that we produce as well. We produce a lot of different alloys, hard alloys as well as soft alloys, and have extensive fabrication capabilities. Today what we're going to do is we're going to take you through a few real-life examples and different things that the different extruders are working on in improving not only our infrastructure, also working on vehicles and improving the impact systems of vehicles and making them safer, as well as working on a variety of life-enhancing medical products that enhance not only patient care but also add to reducing costs. But we will start by overall reviewing just the extrusion process, and then we'll get into some of the different products and applications, as well as some more detail within the aluminum extrusion industry. Obviously, we are aluminum extruders. Our material of choice is aluminum. Aluminum has a variety of benefits to it. Obviously, it's long, strong, lightweight, it's resilient. Corrosion resistance is probably the most key attribute of aluminum. And then when we marry the aluminum with extrusions, obviously we have the ability to tailor the performance or the profile to meet its specific needs. We're able to produce complex shapes. We can apply a variety of different finishes, anodizing, paint, as well as make hollow profiles that are relatively consistent and uniform throughout the production process. As aluminum extruders, I think we all are very much familiar with this particular example, but if you think about it in its very simple form, maybe some of us had the opportunity to have one of these when we were little, or have kids that have had these, but when you think of the Play-Doh machine. So what we do is we basically take a piece of aluminum, we force it through a steel die, and out the front comes the particular extrusion that we're producing. For this particular example here, just basically see the die in the middle. Obviously, you have the billet to the left, and then the extrusion emerging through it. So it's nothing more complex than that. Really, obviously, all the features of the extrusion itself is built into the die and how that actually forms the material. So it's overall relatively simple. However, as we do begin to look at the different parts of the extrusion production line, we do begin to understand that it is more than just a die or more than just the extrusion press. In fact, what we're actually doing throughout the extrusion production process in order to to achieve the different tempers that we're looking for and the variety of different alloys that we produce, at the end of the process, we're going through a variety of heat and cool down cycles to make sure that we're treating that aluminum alloy in the right way to achieve the final properties at the end. So in this particular instance, you see a very basic diagram of most of the extrusion process. There is some additional ancillary equipment towards the end if we're looking at packing and doing things like that. But the actual production of the extrusion itself, we start by preheating the billet before it goes into the extrusion press. So we'll preheat the billet. We'll present the billet to the extrusion press. We will press the billet through the die, and that will run out basically down the table that sits in front of the extrusion press, and then we'll do a hot sawing operation where we'll cut that long extrusion to a piece then that moves transversely to a stretching system where we'll straighten it, and then a finish saw operation where we'll cut it to basically a rough cut length. Extrusions may be processed further and they get fabricated in some way, punched or machined or something like that, so it will be cut down further at that point. But there are some customers that do purchase material that's been sawed right there after the extrusion operation. Those will then go through the aging oven where they'll achieve their final temper, and then they'll be further fabricated, finished, or packed and shipped to the customer. So again, I mentioned about basically the heating and the cooling process. So what we're doing in that, and you can see from this diagram, starting on the left, which is basically down around room temperature. Once we start to move that billet into the billet heater, we're beginning to heat that up, and that process takes a very varying amount of time depending on the diameter of the billet that's being pushed, or the length of the billet, or the alloy, but there always is a prescribed recipe for that particular shape as to what the temperatures that you're trying to achieve along the way. So you can see, starting from the left and moving to the right, that basically you're taking that billet, you're beginning to heat it, and you're getting it to a preheated or pre-extrusion temperature of around 800 degrees. Like I said, it will depend on what the alloy and then also the shape is, what that will be, but it'll be somewhere around in that area. But the final heating that occurs to the shape actually occurs during the extrusion process, which is obviously very much all about the friction, the frictional heat that's put into that extrusion. Now what happens during the extrusion process, obviously we're making the final shape that profile is going to be, but then we're also heating it up to the point where all of the alloying components within that aluminum alloy go into solution. So that time, all of those alloying elements have been uniformly dispersed throughout the cross-section of the extrusion profile, and it emerges from the press. And that will be at an exit temperature somewhere between, let's say 950 to 1,050 degrees. It really depends on what the final temper needs to be, also what the alloy is, and then the cross-sectional area of the profile. But obviously we do not want to basically heat it up so far. If we heat it up around 1,200 degrees, then we would actually melt the profile, and it wouldn't, it basically would be scrap at that standpoint. But between the exit of the die itself and let's say within the first 10 to 15 feet of the extrusion press, then there's going to be a quenching operation. And once you hit that quenching operation, you basically cool that material down that's been put into solution, and you solidify that solution into the profile structure of the extrusion. So that's what's happening in the quench phase. So at the quench time, that could either be air if it's a relatively small, thin-walled profile, to some type of water mist, to sometimes a tank where you actually dump the extrusion into a tank of water if it's a very heavy profile that's coming out. So that's kind of the basics of what's happening during the extrusion process, and we'll come back to this a little bit more as we talk about some of the automotive applications and things like that, where this microstructure is very important to the extrusion, the performance of the extrusion. As I mentioned in the beginning, we'll talk about some of the different challenges and then some of the solutions that face us today. So obviously, over the past several years, we hear different things about the infrastructure and what is needed what needs to be replaced, and then what the opportunities are for aluminum extrusions within that space, as well as, again, healthcare, automotive. All those have some very specific needs where aluminum extrusions tend to offer a significant value within that. So obviously, particularly in the United States today, you don't have to go very far to hit a pothole or even see a bridge that might look a little like it needs to be repaired. So what we do know is that there are over 56,000 bridges that are structurally deficient, which is 9% of the total. So if you look at all that, that's $123 billion of estimated rehab based upon current construction methods today. Now, one of the things about aluminum that we talked about before, it's lightweight, the high strength to weight ratio, it's corrosion resistant, and it also has cold strength. So what does that mean? So in a cold environment, it doesn't become brittle. It still maintains its strength. That's why one of the things that aluminum is used for is for airplanes. Go up at altitude and it's minus 30, minus 40 degrees, and the aluminum is still, flexible, that it doesn't crack, and obviously, there's some type of accident with the airplane. So it's one of those things where we can look at all of these and combining these attributes together and the shapes and how everything will basically work together as a system, to come up with a solution that is actually, I'd say better, can even be more cost effective than what we're looking at today. One of the industries that a lot of extruders, will participate in, does have some type of military application. In this particular application, you have basically a modular bridge that's able to be assembled on site, for foot traffic, moving small equipment, different things like that. But the biggest thing about this is due to the lightweight and the way you can actually design the extrusions, you can actually erect this, in the field with minimal amounts of tools and equipment. So that's, very important to a mobile military. But probably more important to us in the civilian world, is the fact that a lot of these bridges are deficient. One of the opportunities for one of the products designed by a company out there called the Luma Bridge is actually aluminum bridge decking. There's been several of these bridge decks that have already been put in place. There's been extensive studies done in the state of Florida on bridge decks and looking at ways to utilize a bridge deck versus steel grading construction, concrete construction, all the different methods that are out there today. But in the particular bridge example, you actually have several very large extruded multi-hollow sections that are friction stir welded together off-site. So basically, these bridges or these bridge decks can be pre-built in a modular fashion and then moved to the bridge site. So we start to decrease the amount of time that that bridge is actually out of service, which is a very key part when we think about our daily lives and when construction is going on and the interruptions that you face. So in this particular instance with the aluminum bridge deck, you're looking at, a rapid deployment of a bridge. So there's definitely a lot of great opportunities out there to look at aluminum in infrastructure applications where not only will it save costs, because then all the supporting structure of the bridge actually doesn't need to be as robust to take the weight of the deck, but then you also look at the speed at which you can implement that new bridge and basically reduce the amount of disruption to traffic flow. Another great opportunity to talk about is within the healthcare industry, whether it's a patient comfort or a cost issue. We can look at aluminum extrusions as offering a potential solution to a problem. So again, usually with aluminum, we're always talking about the weight implications. So the lighter a component is, typically the less structure it's going to take to hold that, to support that as it's in use. The non-magnetic, non-sparking, non-combustible parts or attributes of aluminum is very important when obviously we're talking about healthcare and parts being in the vicinity of a patient, sometimes next to the patient. Again, with the complex shapes and the fabrication and everything that you can, how you can design an extrusion and then the subsequent fabrication processes to basically come out with the exact part that you need with as little value as possible. So all those coming together will help improve, obviously the patient solution and then also the overall system's cost. Here we have a very, a scanning machine, an MRI machine. In the first iteration of this, there were 64 mechanical levers that had to go to the pneumatic actuators and open and close and deliver that. But they had, because of all the different levers, they had a tendency to break. And therefore, the machine would go out of operation, and I think we've all been, in the situation where we've had to get in for some type of test or something, and then, if the schedule is blown because the machine is down, then you got to rearrange your whole time and try to get back again. So not a very, very comfortable feeling. So in this particular instance, they wanted to reduce the uptime, but they really wanted to reduce their part cost, at the end of the day. So you wanted to make a more efficient machine, and they wanted to be able to build it more efficiently. So in this particular instance, this coupling was replacing an EDM steel coupling. They used a 6063 machined aluminum extrusion that was hard coat anodized. They were also able, because of the extrusion process and being able to basically move the metal where you need it within the profile, they were able to improve the strength and the durability of the part. And then they also had the opportunity, because of the extrusion or the fabrication processes, that was going to build in an identification part. So for traceability, very important. If you do have a malfunction, you'd like to be able to trace that back to the supply chain and see if you can identify any reasons for the failure and therefore make improvements. So in this particular instance, on the bottom, you can see the fully fabricated part, which was actually a snap fit. It reduced the manufacturing cost by nearly 90% and the production time by 75%. So it became, a very cost-effective part to produce. But the more important fact is, through 10 million cycles, it didn't have any failures, which was, provides a lot more uptime for the machine. So not only are the patients happier, but the hospital system is getting more people through the machine, which makes the hospital happier because they're collecting more money at the end of the day. One of the things about extrusions and aluminum is being able to I would say is, speed to market is always very important. Here's a particular piece of equipment that is actually used to aid in the turning of a patient on the bed, which actually is a very time-consuming part for the hospital care staff to be able to reposition the patients. So in this particular instance, there were seven extrusions that were joined together and worked together to actually aid in turning the patient, which they were able to do in 10 seconds versus a longer time than what it had taken before. Obviously, much of the time we start talking about the automotive. Over the last 5 years to 8 years, aluminum has begun to, or has, taken off on a very fast trajectory of being utilized more within the automotive space. Again, within automotive, there's talking about the lightweight. So, vehicles way lighter today. Again, with the high strength to weight ratio, resilient, corrosion resistant. But I think the biggest opportunity within the automotive space is to be able to tailor the performance of the product, which we'll see in a little bit when we start talking about, the crush boxes and the bumper beams and all of those types of energy absorbing components where, again, the consistency of extrusion throughout the process leads to very consistent products which perform in a predictable manner. So it's one of those opportunities I think that we rarely see within a particular industry, and for extrusions there's a great opportunity to continue the growth process as new vehicles are developed, and whether they're an internal combustion engine, a hybrid vehicle, or an electric vehicle, much of the same things or same attributes play into all of those different vehicle types. So here a little bit of information as far as the growth and the projected growth of extrusions within a vehicle, over the last or over the next 4 years, and starting in 2012. But again, you see some of the different areas where they've been used. Obviously, different vehicles, they're all different designs. Again, it goes back to easily tailored. A lot of times, extrusion dies are one of those things that, depending on the size of the die, will really garner the size of the profile. But typically for, relatively complex hollow shape, you could be looking at somewhere around $5,000 to $7,000 for a die, versus sometimes, obviously, in the stamping world, you could be talking about hundreds of thousands of dollars for a die to be able to stamp a part. So it's quite a bit different when we start talking about new tools and what you can do. And also, I think the iteration process is a lot faster within aluminum extrusions than it is with some other types of metalworking equipment, where whether you're talking about castings or forgings or stamping operations, you have a lot more freedom with aluminum extrusions to be able to iterate new designs, because typical lead time for a die might be 5 to 7 weeks, depending on how complex it is and where it comes from. So it gives you that ability to move that process a little bit faster. Obviously, over the last few years, the Ford F-150 has been a great story when it comes to aluminum, and not only the weight savings, but the fuel savings, and then also the safety performance of the vehicle itself. And here we talk about one of the crush cans that are specifically designed. You can see on that upper right-hand picture on the top there, where they're actually pre-dimpled, so they're made to begin the crush process within there. So at the end of the day, look at the weight savings, which translates to fuel savings. Obviously, even the weight savings not only transfers to fuel savings, but then also you talk about less mass of the vehicle, so there's less force to have to absorb in case of an impact. So there's a lot of things that you begin to gain through weight savings and being able to tailor the profiles to the specific application where they're going to be used. Obviously, one of the things about aluminum as a material itself is the recyclability of that material. Since aluminum has been commercially produced, over 80% of all the aluminum that's ever been made is still in use today. And that's one of the things where you start talking about the recyclability of the material itself. So, keeping materials out of landfills is obviously very important, and aluminum actually has a very robust recycling industry behind it that will take that material and it will put it back through the value stream, and new products will be made out of it. In this particular challenge or solution, we start talking about garbage trucks, right? Everybody's garbage needs to be picked up. So in this particular one, we're talking about turning, the dirty diesel garbage trucks into electric vehicles. And how you do that? Obviously, you need an electric motor to do that, and typically those electric motors have some type of extruded aluminum housing around it. So in this particular one, you can see that at a little bit over 5-inch ID on that profile, but all the different small hollows around there to increase the surface area for the cooling fluid for the motor. That's one thing that we do a lot here at Tabor, although this is not our specific example, but we have a large press and we make very large multi-hollow extrusions that are used in a wide variety of motor applications. So in this particular one, you have a 250 horsepower electric motor that's housed in an aluminum extrusion, which are basically on each wheel. So another very innovative way of using the ability to design and put the material where you want it. Instead of having to build something up from a weldment or something like that, we just basically extrude all the features into it. So, in order to do all that, we have to have a good understanding, or at least a general understanding of what solution you're trying to develop. Right? So always, I think any supplier would tell you that early engagement is always good, and through that, your supplier can help you walk through the different, what are you trying to achieve, and then how do we get there, type of thing that would fit, within a production, production process most efficiently. So over the next several slides, we'll go through alloy and temper. We'll talk a little bit about extrusion geometry, get into a little bit of the microstructure, and when we do start talking about some of those structural automotive applications, what we're trying to achieve during the extrusion process. And then lastly, we'll talk about additional fabrication and finishes that are possible with aluminum extrusions. But typically, when we're talking about an aluminum extrusions, we're talking about a 6000 series alloys. There's a wide variety of different aluminum alloys out there, but within extrusion, general extrusion is usually a 6000 series. Although all of these particular, alloys have, can be extruded, they're not always readily available. So within what we typically talk of in aluminum extrusion, it's a 6000 series alloy. Here you can see some of the different availabilities of the different alloys that are out there. Now, this does not include proprietary alloys that a producer might have developed. So these are general alloys that have been registered with the Aluminum Association. You can see there's over 100 6000 series alloys. The next closest right up there is a 5000 series. Those are primarily all rolled. That's all rolled product right there. So sheet, plate, different parts like that in the 5000 series range. 6000 series typically for extrusions, although there will be 2000 and 7000 and 8000 within aerospace applications. Some automotive applications, specifically bumper beams and some of those, high impact type of parts may use a derivative of 7000 series alloy. But mostly we're talking about 6000 series. So within the 6000 series, silicon and magnesium are the primary alloying elements. You can see the difference in the amount of the alloying elements that are put in, and then how that translates to increased strength. So normally in a B and C application, towards the bottom there is 6063. A lot of times that's a good alloy for non-structural components, heat sinks, electrical housing, windows, doors, that type of thing. And we start moving up into the higher strength, the 6082. There we start talking about some of the structural applications for automotive, a lot of marine, non-corrosion marine applications are using 6082. But also where you might see 6082 is if you see basically a transfer of an extruded aluminum product from Europe to North America. A lot of times the Europeans will use 6082 as their kind of go-to 6000 series structural alloy, whereas in the U.S. we're typically more 6005 and 6061. So for the most part, you can see that these aluminum alloys, they're over 97% aluminum. Here's 6063 and 6061. There's not a whole lot of difference when you come to the amount of aluminum in something, but these particular alloying elements, the magnesium and the silicon up top here, in 6061, that's where it achieves that strength. So if we go back to where we're talking about how we heat the billets, and then we put the material in solution as it goes through to the extrusion die, and then we quench it. That's where this becomes very important, because that magnesium and silicon become basically combined mag silicide within the grain structure or the microstructure of the alloy, and that's where you achieve that strength. So usually, well, for the most part, when you talk to an aluminum extruder, they're always thinking about pounds per hour. Pounds per hour for us are what typically dictates price. So the faster we're going to produce something, typically the lower cost it is to produce. But one of the things with the higher strength comes lower production, typically coming out of the press. So that's another thing to be, thinking about when you're thinking about alloy selection and this and that. Do you need something like 6082, which has, a lower extrudability index than 6005A or 6061, right? Is 6060 or 6063, good enough? I mean, that's some of the things that, one needs to think about. And there are sometimes, ways to overcome the strength with extrusion design versus just the material itself. And I think that's one of the opportunities that you can look at when you're designing shapes, is to look at the overall design of it and how does that all play together, and build it into the shape rather than relying on alloy to do it. So usually you always have an alloy temper combination. Typical tempers, F temper, O temper, through the T's, T1, T4, T5, T6. There can be variations on that. Just depends. The H tempers are strain hardened. The 5000 series will have an H temper designation after it. But typically when you're talking about extrusions, you're going to be in the T tempers or F or O temper. So again, a lot of what we do and what we think about when we do think about the extrusion process is we want to think about design and good design practices. What does that mean? So here's just some basic examples of some practices, that you can do. A lot of times the extruder will like to have a uniform cross-section, right? So we like a consistent, uniform cross-section that's balanced. It's going to flow through the die, obviously uniformly, because everything is the same. So it's going to flow, so we're not going to have problems with bow or twists or anything like that. Also, keep in mind that once it does emerge from the extrusion press, it's going to be quenched. So the quench affects a uniform shape the same way all the way around versus a shape that is not. If you have a mass off to one side, that's not going to cool as fast as if you have a mass on one side and a thinner section on the other side. That thin section is going to cool faster, and therefore you're going to get a bow or you're going to get a twist. You're going to get something in the part that may not, lend itself to a more uniform part coming off, of the press line at the end. So uniformity, some symmetry, it's all kind of, around the same type of thought process. We like to keep things even. Transitions, a lot of times we'll get prints as extruders and they'll say sharp corners. Well, these dies are usually made through using a wire EDM, so typically 10 to 15 thousandths is the sharpest radius that you're going to put into something, but that radius is also a place where you're going to build up heat because it's very sharp. You're going to have the aluminum fill out, so you're going to build up a lot of heat in those corners, and a lot of times they're not going to fill out because the aluminum will actually overheat and it'll melt coming out of the extrusion die, so you'll actually get like a tear in there. So smooth transitions, generous radiuses as much as possible. 30 thousandths is usually, good enough depending on, how big the shape is and that. Think about, instead of wide surfaces that don't have a lot of features on it, you are going to pick up the variation, going across, because there is some, just from going through the extrusion press, in a more of a structural alloy, not so much in 63, but, there can be some variations in that surface appearance. So if it is something that's going to be visual, you might want to think about adding some decorative grooves or scallops along the way to kind of break up that surface so your eye doesn't necessarily pick up any imperfections right away. Things can be removed after, through secondary operations, but obviously that adds cost. Here's some examples of, ways to reduce the cost. Typically, a hollow shape, the dies are going to be more, they're going to cost more than a solid die. Multi-hollow dies will cost more than a single hollow die. So in these applications, you can see where, dies have actually been, or profiles have actually been redesigned to take out the hollows, to limit the amount of hollows. And so if you don't need to necessarily enclose the internal void, if something's just going to slot in there, you can definitely, open that up so you don't have additional material in there that you don't really need, because those voids will just add, or the walls forming the voids will just add weight that's not necessary. So there's different options, and all the times the extruders are more than willing to help in looking at the different opportunities to help you save weight and cost at the end of the day. One of the things that we like to look at when we do talk about all the opportunities for aluminum extrusions are these idea profiles. Again, we talk about, different details to be extruded right in, the heat sinks that could be put into an electrical enclosure. You can see around there where you look at some of these fluted surfaces or the scalloped surfaces up top there by the hinge detail, that will help, let's say, improve the cosmetics of the shape, grooves and different slots that you can put in to help, whether it's locate a screw boss that you can actually, screw right into and attach things together. So lots of different ideas to do that. Here's an idea on a heat sink where actually the one on the left is a solid, the one on the right is a hollow. The one on the left was really not extrudable as it was. Yet the one on the right was able to be produced. You taken out a lot of that mass. It's the one on the right is still a balanced shape, but more importantly, in a heat sink application, is surface area. So in this particular one, you've actually increased the surface area because of all the internal voids and made it a more efficient heat sink. Plus you added the details in there with the screw bosses, so you can directly screw onto the to the heat sink with the LED board or whatever goes down there. So it's not all the time that hollows are necessarily not the right solution. A lot of times they can be the solution and turn something from really a not extrudable part to a producible piece. Here we'll talk a little bit about geometry and some of the things that that you can look at to offset the limitations of the alloy. Here is a very interesting one when you look at the chassis tub. You see the first of the upper left-hand corner, where that is actually 60/60 alloy. And if you remember, that was probably one of the most softer 6000 series alloys that we have. Typically not used for structural applications. Same thing here on the front subframe. Basically everything in green on the car. So it's very interesting that you can actually do that. Adjust and use geometry versus the metallurgy to create the part that's needed. Again, you get an idea of what some of these components look like. Are very purposefully designed for that part of the automotive and how it has to perform. So again, we start talking about microstructure, what we want. It's very, very important when we're into automotive applications. It would be good to understand what the material strength is. How you're going to join it. You're going to crush it. You want to machine it. The surface characteristics. So all of that is important when it comes down to alloy selection, temper selection, and even selection of a vendor. Because a lot of times not all extruders are created equal, and different extruders are capable of producing different types of shapes. But at the end of the day, we're looking for these grain structures that really are the way that the shape is enabled to perform the way it does. So, and again, we come back to quench is very important. So we can do everything that we want. The alloy can be right on. We could get everything through the die as we need to. But if we can't quench that part correctly, it's not going to come. It's basically not going to be correct after we've gone through the tempering cycle. So again, we come back to heat, the billet heating the press, and then the quench. So very important when we talk about it. And again, an extruder is always going to have that in mind when they're looking at your shape to understand what they need to do. So right in between, as I mentioned before, here's the same line, or the same press line in a lineal fashion is right in here. Number 2 is where that quench comes in. So it's right after the mouth of the press. It happens within the first 5 to 10 to 15 feet, depending on the size of the press and the type of the quench that it is. But it's extremely important as we look through how we produce the final alloy and temper. So again, here's more of a chart that talks about the recommended rate of cooling. So every alloy has a different cooling rate as it comes out of the press. As we start to wrap up here, we get into some of the different let's say value-added opportunities beyond aluminum extrusion. So there's we look at fabrication and finishes. Finishes, you're talking about painting, wet or powder, anodize, all the different architectural shades and colors. Mechanical, talked a little bit before about some of the aesthetics in some of the extrusions, we can brush them, we can polish them, we can do different things to them to make them look nice, and then obviously applying different types of stickers, and there's all different kinds of appliques that are put onto extrusions. Finish is a very important part of understanding what alloy is needed. Not all alloys anodize the same, so that's one of the things. So if you have an idea of what type of finish needs to be on the part, in its final application, that would be a good discussion point in the beginning. Fabrication, there's a wide variety of different fabrication types: CNC machining and bending, simple punching and cutting, just friction stir welding. There's a whole world of fabrication out there, and most extruders offer at least some type of fabrication. But here we look at basically a weldment for a tent pole, for a military tent, where you look at the extrusion that's then built up with the stamped part, and then painted in its final assembly process. But all those different sawing, punching, machining, bending, welding, milling, tumbling, it all goes into basically that one part to come out to the final process. So in the end, it's really all about what do you want? Where do you want to get to? And then we can talk about what's the road that we take to get there. Definitely have a lot of opportunities, as we discussed earlier, with the different automotive, medical, infrastructure applications, but it's really a world of opportunity out there when you start talking about saving weight and improving the products and making them last longer. So at the end of the day, I think all we ask is, as aluminum extruders, we want to help you. So if we understand the combinations of the alloys, the geometry, the microstructure, the finishes, and the fabrication, all that, how it works together, it'll help us help you, create the best solution that you can. But as always, early engagement, early involvement, leverage our experience. Chances are we've been there before, we've seen it, we've done it. We can help, steer through the world of possibilities. And as I said before, aluminum is fully recyclable. It's a great way to improve your environmental footprint. If you do visit the AEC.org, there is an EPD out there that is fully downloadable on the extrusion industry. If you're more on the architectural side of things, we do have a life cycle assessment as well that's available. So, all those are industry publications available to you. Again, AEC.org, there's a lot of information out there. There's design manuals. You can even search for an extruder if you don't have one, or search for a different one if you need one. Lots of different resources there to pull from. And then the Aluminum Association publishes the Aluminum Design Manual, the current 2015 edition, and that goes through everything having to do with aluminum extrusions and other aluminum products as well. Mentioned before the fair trade activities of the Aluminum Extruders Council. We also interface with the Aluminum Association as well as some other industry associations. AECfairtrade.org is a place to go to get more information on a wide variety of activities that are going on today having to deal with trade. Appreciate all of our members for supporting today's webinar. Again, my name is Jason Weber, Vice President of Sales and Marketing for Tabor Extrusions. And I appreciate it, and I'll throw it back to Paul.
All right. Thank you, Jason. We are now going to use the remaining time for questions, and we certainly have had some that have been coming in, but it is not too late to send in your question. Simply use the dialog box that is located on your screen. All right, Jason, if you're ready, first question. Clearly, very small differences in the quantities of alloying elements can have a real impact on properties. How is this managed, especially when a lot of scrap is used?
Well, so all of the aluminum alloys, the Aluminum Association is the governing body for aluminum alloys. So what happens is they basically publish the chemical requirements of the different alloys, and the alloy producer is going to meet those ranges within that. So to a certain extent, there's a lot of times where scrap, as long as you know what the alloy is of the scrap that you're putting in, it doesn't have any effect on the final alloy. And all the secondary producers are going to buy from certified scrap dealers that are going to report, what that is. So
All right. Next question. I have seen issues with anodizing of cast aluminum due to the high silicon content. Is this an issue with any 6000 series alloys or extrusions?
Not like it would be on castings, because castings have a much higher silicon content than the 6000 series extrusions do. But within the 6000 series, there are some that anodize better than others, and particularly 6060 and 6063 would be readily available as alloys that are better for anodizing. There's also a couple other specialty 6000 series alloys that are better for anodizing than that, but usually as a general purpose, 6063 or 6060 would be best.
Okay. Next question. What is the thickness range for extrusion?
It really depends on the size of the press. Here at Tabor, we have two micro presses that run 2.5. The smallest is 2.5 diameter billet. Depending on the alloy, we can get as thin as 0.010 of an inch. In general line extrusions, probably maybe 45 thousandths of an inch is the bottom of what you'd see. Here at Tabor, we also have a very big press, and we can go, we can do 9 inches in diameter on a round. So, yeah, really in that you're limited in your ability to solution heat treat when you get thicker, but you can run. We can run parts up to 140 pounds a foot.
Okay, one of our viewers wants to know how can they get basic knowledge in calculating the strength of an extrusion? Through the believe in the aluminum extrusion design manual that I put up there. So AEC.org, just search for the design manual. I think there's some basic calculations in there. If not there, then the design manual for the Aluminum Association would be a good go-to guide for that. Okay, perfect. What is more cost effective, 6066 or 6063? I would typically say 6063 is definitely more readily available than 6066. I'm not overly familiar with that alloy, but the more readily available something is, typically the more cost effective it's going to be. 6063 would be that. Okay. Here's a question specifically referring to your slide number 33. And they're wondering why the screw boss is slotted instead of solid. Let me go back to that. We can. 33. There we go. I think that one's probably more of a matter of preference. Usually a screw boss, like what you would see more in
This particular slide with the big heat sink where you can see the screw bosses in the middle, those are meant to receive the screw from up top. So basically going into it, let's say in this horizontally, whereas the screw boss that's depicted in slide 33 on the bottom there, that could receive a screw along down the length of the part from basically underneath. So it's just a matter of what direction are you going to be fastening the screw from.
All right. Can you give a little more detail into how geometry can improve strength? Maybe an example?
I'm just trying to think if there was really a good example. I think a good example of strength as far as, let's say, bending, if you're looking at bending along the cross section, would be the difference in an I-beam versus a rectangular tube. If they're both standing up, long direction up, the rectangular tube, because you basically have two vertical walls, is going to be a much stiffer part than an I-beam, which typically only has one wall. So a lot of times, even if you make that, you can achieve the same strength with the extruded hollow rectangle than you can with an I-beam that's usually bigger and taller and wider. So it's and I think even within the probably in the aluminum design manual from the Aluminum Association, will talk about the strengths of beams and the differences between how to calculate on a hollow versus a beam.
Okay, can you talk a little bit about some newer applications for extrusions in automotive?
Newer applications. I think a lot of times we're seeing a lot of more. Not only the structural parts like the front, things like bumper beams and crash boxes, but now getting more into, the, I don't know what I want to call them, the understructure of, the sills that go alongside and some of the cross members that can be underneath the truck or underneath the, on the back of the vehicle. I guess I'm not an automotive engineer, so I can't talk specifically about part names, but a lot of times it's things within that. It's also the integration now with vehicles and electric vehicles and what's going on. It's integration of the battery boxes and integrating cooling features into those battery boxes or into the motors, as we looked at before with that example from the garbage truck with the garbage truck motor. It's really becoming not only being used more prevalently in different parts of the vehicle where you might replace the stamped part with an extruded part, but then also the integration with the different features and cooling features that you might need in an electric drive of some type like that. So definitely with the advent of the electric vehicle over the last 5 to 8 years, I mean, we definitely see a lot more electrical cooling and applications than what we have normally seen before.
Okay. What is the maximum aspect ratio of heat sink fin gap to fin height that you can extrude? I have seen examples that are 13:1 and 16:1.
Yeah. Typically the aspect ratio on a heat sink is, there are two different types of extrusion presses. Direct press, which is really what I talked about before. You basically take the die or the billet and you force it through the die, and an indirect press, which is basically taking the tool and almost pulling it over the billet in a way. And with the indirect process, you can definitely get a lot higher aspect ratio out of the heat sink. So it is, I have seen, 16:1. I don't know, and those are off of indirect presses. I'm sure they've probably gone, surpassed that. I don't know, but normally within direct extrusion presses, I mean, on Tabor's big press in Russellville, Arkansas, we would probably be lucky to get 4 or 5:1 aspect ratio out of it. So. But yeah, definitely 16-to-1 is doable for the right extruder.
Okay. All right, Jason, one last question here. Can you expand a little bit on the higher cost and less availability of 7000 series extrusions, especially custom extrusions?
Yeah. Well, a lot of times the availability comes into just the alloy itself. It's very high in zinc, and zinc is actually a contaminant. So, you really have to be set up just to cast 7000 series because of the zinc, because you don't want that contaminating your entire scrap process. But then also, if you go back to reference back some of those slides we were talking about microstructure, it is also a much harder alloy. So it's a lot slower to push, and it's a lot harder to push. And that has an effect on what you can actually, the types of shapes that you can actually make with it. There are some 7000 alloy variants that are very low in zinc, and are lower on the strength scale that you can make hollows with, but your typical 7050 alloy that you're going to see in a lot of applications for aerospace is not a very extrudable alloy. So it's a combination of just alloy availability of extruders that will want to push it, and then the production rate at which it's going to be produced at.
Okay. Well, that's all the time that we have for Q&A. If you do have additional questions that come to mind, you are welcome to email those to me directly at pheaney@wtwhmedia.com. Thank you, everyone, for attending this webinar from Design World and our sponsor, AEC. This presentation will be emailed to everyone in the coming days, and it will also be available then at designworldonline.com. Thanks once again to Jason for all of his insights. Have a great rest of your day, everyone. Goodbye.